It's great to be here again. I think Dan Friedman and I spoke at an unsession at the con 5 years ago. And since then, the Clojure community has been by far the most supportive group of the work we've been doing. And I think it's accurate to say that what you're about to see wouldn't exist if it weren't for the Clojure community. And folks like David Nolan and his work on core.logic really gave us a big boost. And Stu Holloway's infamous question about quine generation has basically driven my research for the last 4 years. So I'm, seriously, thank you. I think this is an amazing community, and I found it super inspirational when there have been times where academia hasn't always been as supportive as, academia, part of their job is to throw rocks at things, and they're pretty good at it. But the Clojure community's enthusiasm is really what's driven this. So what you're gonna see wouldn't exist if it weren't for you all. So thank you. So introducing Barliman 4.3. And inspired by Rich's talk, we have decided to go with an immutable versioning scheme. So at all times in the future, this will be 4.3. I think that was the takeaway, if I understood it.
Yeah, you got it right.
And so what we're going to try to show you is sort of what Dan and I were trying to show off five years ago, part of the vision. And we've gotten better, and we've hidden a lot of the details that you may have seen if you've seen some of the previous talks. So you can forget for a minute at least how this is working under the hood. If you know how it might work, kind of erase that from your mind. Let's just think for a minute what an interactive development environment might look like, or what capabilities it might have in the future. So think about what your IDEs can do today, and we're going to try to give you a little bit of a teaser of how we think an IDE might work in the future, and hopefully not far future from now. And we're not going to show you everything that we think an IDE should have, but we're going to show you a couple things that we think are interesting. And what I'm going to ask you to, I'm going to ask your indulgence and ask you to look at this as very much a prototype. This is an idea talk. We're trying to show you some things that might be possible in either the midterm future, or hopefully some of these things I think will be available in the near-term future, like within 2 years, some things maybe within like 6 months. And it's also very much an appeal to you. If you find this interesting, we could use your help. We could use your help. I would love to have a version of this in Clojure using core.logic. And there's a whole bunch of tasks in terms of interface design, interaction design I think are really interesting, language design, all sorts of implementation details. Really interesting work, I think. And so if this appeals to you at all, please let us know. All right, so without further ado, Greg is going to define concatenate. Okay, this is all in Scheme. We've tried to use Clojure names to confuse me, but we'll see how that goes. But we're going to define concatenate. So Greg, please define concatenate in the most natural way.
All right, I'm done.
Okay, comma A is concatenate, of course.
Of course.
And you can see that Barliman took a guess at filling in whatever comma A means. So the A is a metavariable. It represents an unknown expression. And down below in the best guess window, you can see that we get clearly the definition of concatenate. Now, we might want to try a test.
Yeah.
Let's try a test for concatenate, make sure this is the concatenate we actually want.
Right, so like a diligent programmer, I will test my code before I inflict it upon other people. So we'll start with a simple test case, concat on 2 empty lists. Should give us the empty list.
Okay, so now Barliman is saying that it thinks this function is called concat. And in schemely notation, it's saying that it can take any number of arguments. It's a variadic function, and it always returns the empty list. Okay, so far that passes our test. Great. Perhaps we should add another test before we ship it.
So we'll concat a list containing 1 and a list containing 2, and we should get a list containing 1 and 2.
Okay, so Barliman has synthesized a more sophisticated program. Now Barliman believes that the function probably takes 2 arguments, and it's doing a null check on the second argument, in which case it will return the empty list. Otherwise, it returns what's clearly the answer based on the test, which is the list 1, 2.
Barliman is very lazy. It finds the path of least resistance to satisfy your examples. So
Barliman's view is prove me wrong.
Yes. So we have a technique for getting around this, which is to use specially generated symbols that Barliman is not allowed to write into the definition.
Yeah, so let's generalize over our inputs of 1 and 2 and try to make it a little more generic. So these are essentially gensims or lexically scoped gensims, these G1, G2 things. We're saying we don't actually care what the data is. That should be unimportant in the function that you're trying to generate for us.
So we have a new result?
Yeah, so now you can see CanCat is no longer specializing over the inputs 1 and 2, and instead it's going to have to use cons and car. Okay, so car to people in the Clojure world, that's how you take apart part of a pair in Scheme. And we don't have all the fancy pattern matching, although Barliman actually does support pattern matching. Okay, now, is there anything missing with this definition? What's missing with that definition of CanCat? Would you be happy with this definition, CanCat?
I see heads shaking, so.
No? What's wrong with it? A list with something else also? Well, it's an empty list and list of something. Well, so basically what we're missing is recursion, right? We don't have a case that will allow us to do this with a list of arbitrary lengths when the first list is arbitrarily long.
Right.
So, time for another test. All right, so Barliman will think for a minute here. Help us make this faster.
Yes.
Okay, now we have another definition. So Barliman now thinks that this should be a recursive definition. And we have these weird looking variable names, _1, _0, and those are abstract variable names. The idea here is that we don't actually have to know what names they are. We can instantiate those to any legal scheme identifiers.
Yeah, I can clean those up though, so I'll do that now, just to make it slightly easier to read.
So Greg's putting in another variable here, _a. And the idea of this the comma a is a hole. Okay, so we have a hole in our program. We have a partially specified program by the programmer in the definitions window, but it has a hole in it represented by this meta variable, a. And now you can see, because he instantiated the variables, that we can see the actual variable names in the definition. And furthermore, you might have noticed that the synthesis was faster. And the reason it's faster is that now Barliman knows for sure that this is a function that takes 2 arguments. And actually it knows the concrete names, which in our current version speeds it up a little bit. If you look at the tests, you can see that we could do better because we should be able to take a reasonable guess that this is a function that takes 2 arguments. Right now, Barliman doesn't really know. It's not using that information. And one thing that we'd like to do is have a version of Barliman that has a backend that can run in parallel. Get an EC2 instance, get 10 of them if you want, run 1,000 threads or something like that with different Barliman searches running in parallel with different heuristics, with the idea that maybe you'll get lucky. And if you get lucky, because this is inherently an exponential problem, if you get lucky, you get really lucky. It's way faster. So using heuristics is something that would be good here. Okay.
So I'll show you another neat thing we can do. So in a more realistic setting, you wouldn't be defining something like this in a vacuum. You would often have access to some kind of standard library. So to sort of simulate that, I'm going to paste in a definition of what we call reduce right. You can think of this as a reduce that goes right to left, rather than the standard left to right. And you'll notice that almost, I didn't even notice that it did it. It synthesized a result for CanCat in terms of reduce right. Down here. So another thing that we can do is if you were to be given this definition of CanCat in terms of reduce right, but you didn't happen to have a definition, the definition of CanCat in terms of reduce right, but you didn't have the definition of reduce right, you could actually use this definition of CanCat to synthesize reduce right. We won't show that now because it'll take a little bit of time and it involves some monkey work. So let's move on to something.
So so part of the problem is we have a lot more capabilities than we're exposing currently. So this is got sort of a UI challenge and just sort of an implementation challenge. So that little scroll bar thingy, I implemented that at 3:30 this morning. So we're still working on this.
So we'll go for another seemingly simple definition. We'll try to reverse a list now. So reversing the empty list, of course, gives us the empty list. Reversing a list of size 1 gives us that same list. Very interesting. And Barliman seems to be handling this just fine so far. Oops. Now we will try to reverse the first interesting list. And we'll notice that Barliman's having some trouble. I'll give you a spoiler. It's never come back for me. I've sat and watched for a long, long time.
But you can try it at home.
Yes. So there's an unfortunate wrinkle with the definition of reverse. Barliman seems to prefer to define things in a naturally recursive way, very directly. But if you've tried to define reverse for yourself before, you might know that there are some issues with that. I'll show you what I believe is pretty close to what Barliman is trying to synthesize here, which is reverse in terms of CanCat. Now, if you've studied this definition of reverse before, you'll know that its time complexity is quadratic in the length of the list, because each of these iterations does a CanCat on a list of length n-1, then n-2, and so on. So you add all those together and you get something quadratic. So unfortunately, the way that Barliman is currently implemented, the computational expense of a particular solution impacts how far down the search tree it will find it. So it's actually much harder for it to find a definition like this than one that would be linear time, for instance. So one thing to wonder is, let's say you're defining reverse. We'll go back to this template. And you're sitting here, it's taking forever, and you wonder what's going on. Maybe it's at a bad mode, and it can't find a solution without your help. One thing one possibility is, one way to speed up recursive definitions is you can sometimes pass an accumulator, and thereby avoid constructing and deconstructing the same representation over and over. Instead, you're just passing a state to the next iteration. So let's based on the hypothesis I just shared, let's hypothesize that there's some reverse ACK which takes some accumulator, and we don't really care what it does with it. And we'll just define our reverse in terms of that and see what happens. We'll assume we can pass an empty list as the accumulator. And pretty quickly, Barliman comes back with an answer.
So the idea of Barliman is that program synthesis is hard. Recursive program synthesis is especially hard, especially without static typing and things like that. So we're playing in hard mode, although we do have one great advantage, and this is an advantage that Clojure has, is that we have pure functions. We believe in immutability and things like that. So if you're dealing with pure functions, it makes it much easier. And I'd rather actually have the pure functions than have types and have mutation in terms of the synthesis for sure. But because this is a difficult problem and it's inherently exponential, the idea of Barliman is we want to experiment with something interactive when we have the programmer in the loop, and the programmer can just use this as an IDE. Here we're trying to show synthesis examples by example, where you write the tests and then you get the program, but that's not really how we envision most people using Barliman. It'd be more like you're writing your program, and if you followed practices of test-driven development or whatever, you have generated tests, you can have a bunch of tests, and the tests can help you. So one thing they can do to help you is try to synthesize missing parts of your program. And so maybe it's the case that it's too slow to synthesize most of your program, but maybe you can give it a little bit of help like that. Or maybe you can write 90% of the code and it fills in the last 10%. So think of it as sort of like maybe an autocomplete that understands the meaning of your program and not just things like the types or the grammar. So sort of a semantic autocomplete. That's one use case we have. We got some other use cases we're going to show you as well, but that's one of the ways I can think of it. And so one of the questions we have with Barliman is, we're trying to answer with Barliman is, well, how well does this have to work in practice to be useful, to be worth using this sort of IDE? If you could get autocomplete for the last 10% of your program, would that be sufficient? How well can we scale this?
So I'm going to just show them one more neat thing you can do. So now that we have a definition of reverse ACK, let's, just for fun, we'll synthesize the driver using it. So we'll replace this with what we just synthesized, and we can see we can also go in reverse and synthesize the driver using it. So just a neat thing. So let's show a slightly different example. So suppose you have some data you'd like to transform. You have a list of them, maybe nested structures of some kind. You might use map to do this. So suppose we have this a nested structure that looks something like this. So we have 3 elements. The second one happens to be a nested list with 2 more elements. And let's just say we're interested in, for each of these nested structures, we're interested in grabbing the first item of the second item. So in this case, it would be B, and in this case, it would be 2. So often you pass something like a lambda or a predefined first-class function to map in order to do the transformation. Here we'll suppose that we're going to synthesize some kind of lambda, and we're interested in seeing what the body of that should be. So we'll say that this should be equal to bn2, as I explained before. And Barliman figures out that the lambda should look like this. So it picks apart the nested structure in exactly the way that we were hoping it would. All right, let's look at another one. Let's do remove foo.
Okay, so here's a simple recursive definition in the spirit of the little schemer. And what remove foo is going to do is going to take a list, potentially nested list, deeply nested list, and it's going to remove all of occurrences of the symbol foo from that list and give you back a list with foo removed. So we'll get a few tests here for remove foo. Hopefully it's pretty clear what remove foo should do. And it turns out that remove foo is not something that we can currently synthesize. Hopefully we'll be able to do it in the future, but this is also something where generative tests might help. But we're going to show a somewhat different use case. Say you have a definition, and this is more realistic, I think. So you have a definition you're not going to be able to synthesize directly from a specification or from tests or from properties or whatever, or from types. If we could add type inference to Barliman and use that for synthesis as well. We could add all these things. But in practice, you're probably going to have to write most of it as a programmer. And so what Greg's doing right now is he's pretending to be sort of a structured editor. And he's trying to keep legal S expressions at all time. And he's adding these meta variables to keep the structure correct. And so he's just going ahead and adding the base case for remove foo. And you can see the .a at the bottom, that's saying that's some unknown number of additional con clauses, 0 or more. So we're saying that this program could have an arbitrarily large number of con clauses, could have 1 million of them or whatever. And so he's written a certain amount of structure now. And so he's got cons BC. So we have 3 different holes in this program right now. We got the B, C, and A. And the interesting thing here is that even though we've only partially specified this program, we can fail a test. So the second test fails, and what that's telling us is that there are no expressions in our subset of scheme for which filling in B, C, and A would actually make that test pass. So the idea is we can do test-driven development on partially specified programs. And I think once we add the capability of doing generative testing to this, it will be way more powerful. And this is something that I think we could make practical relatively near future. And I think that would be a pretty cool capability for IDEs, is the ability to do this. And I think Clojure would actually be a particularly good language for this, especially with things like core spec. So what I would really like to get to the point where we can have core spec style properties that you would specify, and you'd be able to run contracts on partially specified programs and things like that. I think that would be a very powerful way to do development. And my hypothesis is if you had those sort of rich properties that you wrote first, you would be able to keep yourself from going down dead ends many times early. This is still a hypothesis. We don't know in practice how well this will work because we're still developing the tool to the point where we can do these sorts of things, but I think it would be helpful.
All right, now let's have some fun. These have been kind of straightforward and boring so far. We're going to play with a little evaluator written in Scheme for Scheme.
Is Stu here? No? All right, this is Stu's fault, this example.
So we have a very simple definition of eval. It can construct some literal data. It can make first-class functions, reference variables, build pairs, and apply functions. So not much to it. Maybe an interesting thing to note here is the tower of interpretation. Do you want to describe this?
Sure. Well, why don't you do the example first, and then I'll explain that.
All right. So I'm going to set up this query to run while we explain what's going on.
Okay. Get it running?
Yep, it's running.
Okay, so what we're currently doing is we're trying to generate.
Oh, by the way, how many people have seen Inception? All right, keep going.
Does anyone know what a quine is? Some people here should. Okay. So a quine is a program that evaluates to itself. And Stu Holloway, I guess about 4 years ago, suggested that the work we were doing, we should be able to generate quines just from the mathematical specification. And it turns out we were able to after a lot of work. That's sort of driven my research, that little observation. So here we're doing the same thing, but we're doing it in a slightly different way. So we are trying to generate a quine, a program that evaluates itself, in this little subset of Scheme. But the way we're doing it is we're using this eval function, which is a Scheme interpreter written in Scheme in a higher order way with using procedures to represent environments and closures. So this is a higher order recursive definition of evaluator. This Scheme interpreter, which is generating a Scheme expression, which is a quine, is itself being interpreted by a Scheme evaluator written in the miniKanren constraint logic programming language, which is itself written in miniKanren, which is itself written in Scheme. We can go significantly deeper, but this is sort of like a good starting point. So this is the quine that we've generated according to sort of Stu's suggestion that we can generate quines. It's a little bit slower because we're going through all these levels of interpretation, and this is an open problem that we're trying to work on, is trying to do things like partial evaluation and super compilation to get rid of most of this interpretive overhead. And it looks like there are things we can do to speed this up. Okay.
Just to convince you that this works, by the way,
Yeah, prove to us
I'll
that
run
that's
it in
applying.
a scheme interpreter. So this is really a scheme interpreter. Look, I can add things, and it does what you think. So
Very sophisticated.
yes. So here I'll just copy this guy that we synthesized, and it returns itself. So it seems to do the right thing. So let's show another fun example.
Yeah, let's.
We have a little more time. So this one is going to be a proof checker for a very simple logic.
This is based on a proof checker that Matt Might wrote. And he wrote it, I think, for a paper we were writing. And so he wrote a little tiny proof checker for propositional logic, a very weak logic. And he just wrote it in Racket. It was like, hey, yeah, we get this little proof checker. And Greg has extended a little bit to make it a little more interesting, but it's still written in the same spirit. And if you take this code and you run it in Racket, it runs forward. The way that this works is that you have to give it a proof of something. You have to say, okay, here are my assumptions, here's the thing I want to prove, and here is the explicit proof saying exactly which rules of inference I'm using at each step. If you've ever taken a course in mathematical logic, these are the sorts of things you do by hand where you have to say, okay, now we're using modus ponens, and here we're using modus tollens, or whatever. Here we're using an assumption.
It's a real pain.
Yeah, it's a real pain. So that's an example proof. They look like that. And if you've ever taken a logic course, you spent hours doing those by hand. So anyway, Matt just did a little proof checker that would check that these proofs are correct. So we've taken that code without modification. This is the same code you would run in Racket. It was intended to run in Racket as a function.
So just to give you peace of mind, just to make sure that this test actually does succeed. So this test is attempting to check the proof that we've handwritten here. So test should return true here. And Barliman agrees, so yeah, I'll trust it.
That little define answer thing, that's the hack that Greg had to invent because we're not exposing all the behavior of the underlying miniKanren system yet.
Right, so we're synthesizing dead code to pretend that we have like a query system.
Yeah, but we're going to add a real query system soon, so you'll be able to do this a little more naturally. But so you can kind of ignore the answer thing. That's sort of a hack because our interface isn't expressive enough yet.
So if you've picked up on our theme so far, you probably can anticipate what we're going to do next. We're going to take this proof checker, and we're going to give it the conclusion and the assumptions, but we're not going to tell it how to prove our conclusion. We're just going to leave it up to Barliman and see what it does. We're going to tell it that this proof should really be a proof.
Yeah, you have to say that the proof checker should return true, otherwise you will only generate incorrect proofs. We can do that as well. I mean,
yes,
it sounds funny, but being able to generate almost correct proofs is actually really useful because this is an example of the sort of thing we can do with test generation. And I think that's another thing that we'll be able to do practically in the near future. You often want to be able to generate programs which are almost correct or almost have some property, but not quite. And so that's the ability to be able to enumerate incorrect proofs is actually potentially useful.
So if we look at the result, we can sort of compare it side by side. If you do a visual scan, it looks like it synthesized the same proof that we had handwritten before. So it seems to do the right thing. You'll notice that in the original code, we were just stubbing this out, so we didn't cheat there. This thing really works. We can prove more interesting things as well. Let me pull up a few ideas. So here are a bunch of things we've proven so far using this particular proof checker. A fun one is this commutativity of hypotheses. The idea is that if A implies that B implies C, then also B implies A implies C. So we should be able to prove this conclusion. Let me get rid of this. So now we should replace our answer with a proof of this. Oh, that's not what I expected.
I don't think it's running.
Oh, sorry, I have to actually say what C is. That's kind of important.
And C is the thing we're trying to prove.
Right, C is the conclusion. So this thing is C. Or I can actually do it this way.
It's great fun running these queries because you never know if they'll actually come back. You know, you're one missing comma away from not.
So it'll take a few seconds.
Or it will take forever.
Or I might have written something wrong. Yeah. Oh, it seems to have come up with an answer. So we can take a look at this.
Lucky day.
So here's a proof of the conclusion we were just trying to prove. I looked at it offline. It seemed fine to me. You can verify it for yourselves. So, yeah. Do you want to stop it here? Ask if they have any questions?
All right. Let's stop there. Actually, let's talk for a second maybe about kind of where this might go and what ideas we have.
Yeah.
A couple of other ideas we'll mention. First thing I could say is, we're not the only people exploring program synthesis. And there are a lot of people exploring program synthesis in various ways, and we're not even the only people exploring interactive program synthesis with like an IDE. There's lots of work I could point you to. In fact, we need to update the Barliman webpage to try to point to some of this existing work. One piece of related work is by Peter Michael Osera. He's got this type and test-driven development system that's really cool. And there's a whole bunch of interesting systems out there, Leon and so forth. There's been a real renaissance in program synthesis in the last, say, 5 years, and I think you're going to see a lot of interesting work in this space. The thing that makes Barliman different, I guess, is our philosophy. Our philosophy, I think, is very much Clojure and very much like core spec, which is why I like to design core spec so much. Is it, I guess Stu described it as a la carte, I think was the term he used, where the idea is that you can use whatever you want, but the system's never going to require you to do anything, right? And so Barliman has the same idea. You can write tests, and the test might help you synthesize some missing code. The test might help you refute the code you've written, saying that this is incompatible, what you've written is incompatible with a certain test, no matter how you fill it. Those are useful things, but if you don't want to write any tests, you just want to hack away, that's fine. It will degrade to a standard text editor. If you want to add types and a type system and type inference or type checking, it can handle that, but it's not going to require it. In fact, if you added a type system on top of this, say you did sort of like an ML version with S expressions as your language, then you could actually specify partial types. You could say, this is a function that takes an int and maps it to, I don't know, I don't want to think that hard, just fill in whatever. So you could have partially specified tests, partially specified types, partially specified properties, partially specified definitions of your program, and Barliman will just take all that information and combine it and try to help you. But it's never going to require you to do anything, and that was one of the main points that we had. We wanted to be very easy for programmers to use. They can use as much or as little capabilities as they want at any time. And then the other idea was we wanted to make it feel interactive and feel fast so that the programmers could just use it as an editor, and every once in a while there's a happy surprise and it fills in something or says, no, you're wrong. Computer says no. You're going to have to rethink this partial definition.
Before you've written the entire program.
Before you've written the entire program, right? So our view is true test-driven development, you not only write the test first, but the test should be running all of the time as you're writing the program. It should be constantly running in the background. And so ideas we have, better heuristics, better search, better parallelization. One of the things that Greg did was over a 6-week period, he sped up these synthesis queries by about a factor of 1 million to 10 million. And it's like, I didn't get you anything, Greg, but that was appreciated, thank you. And it seems like there are a lot more techniques that are out there for program synthesis that we could apply. So, we've sped up, between that and some other changes, we've sped up program synthesis by a factor of probably 10 to the 7th, 10 to the 8th, more than, faster than what you saw 5 years ago when Dan and I were giving demos. I think we can conservatively get another factor of 10 to the 6th, another factor of 1,000,000. And I think it's likely we can get another factor of 1,000,000 after that. When you're dealing with an inherently exponential space, that doesn't mean you're going to synthesize a 100,000 line compiler. It means that you can do modestly more capable, larger programs and more complex programs. But it's enough where I think it's starting to become interesting. And especially with the testing technology and the ability to refute your code as you're writing, I think as we make that faster and more capable, that is something that will be practical near term. Do you have any comments or?
No, I think you said it all. Another nice thing about exponential problems is you can always keep making progress. You're never done.
Yes. Greg sped it up 10,000 times, and now we're only dreadfully slow, that kind of thing. Yes.